Hi all, Dr. Clark here again. Today we're going to talk about molecules and bonds. Okay, we just left off. We were talking about just general information about chemistry. Okay, and we were talking about atoms and elements and isotopes and ions and electrons, protons, neutrons. Okay, just a real basic chemistry that you'll need to know. Okay. And today we're going to go a little bit more in depth. This part of the chemistry is more about what happens when you link two atoms together, two elements together. You make a molecule. Okay? What's holding those molecules together, and then what unique properties do certain molecules give us. Okay? For example, here you can see DNA. Okay? DNA is a very unique molecule. We'll spend a lot of time on DNA, but one of the nice properties or unique properties of DNA, okay, is that DNA in the center where the nucleobases bases are going to be, okay, will always have a three-ring structure, okay? Because guanine always binds to cytosine and adenine always binds to thymine. So you're always going to have a three-ring structure in here. That keeps DNA kind of a uniform double helix. Okay? We'll come back to why that's important and what that allows for the structure to do when we start talking about DNA. Okay? Alright, so let's talk about molecules in general. So again, molecules are just a group of atoms, okay, held together by some kind of energetic force. Okay? And it can be 2 atoms, it could be 50 atoms, 100 atoms, whatever. It doesn't really matter, okay? But nonetheless, they're held together by some energy. Sometimes they can be held together by multiple energy forces. Okay? That energy that's holding those atoms together is what we call bond energy or chemical bond energy. Okay? And for a biologist, this is very important because what chemical bond energy tells a biologist is that if you break that bond, if you separate those atoms, energy is going to be released. Okay? So if this bond or molecule that you're talking about happens to be a food source, we know that if you can break down that molecule, say a carbohydrate, and you can break it into smaller pieces, every time you break it into smaller pieces, the potential for energy is there. Okay? And that energy can then drive work and is what powers a living organism. Okay? Now there are 3 main types of chemical bonds. Okay? Ionic bonds, covalent bonds, and hydrogen bonds. And we'll go over each one of these. And now there are other bonds and there's other forces that can hold atoms together. Okay? But remember, this is a biology class, and in chemistry you're going to go much more in depth on these issues. This is just enough chemistry to get you into being able to examine biochemical pathways or conversion of energy and things like that. Okay? So first, ionic bonds. This is the attraction of opposite electrical charges. Okay? So if you have one atom that has a negative charge, okay, meaning it has an extra electron, and then another atom has a positive charge, so it doesn't have enough electrons or has more protons than it does electrons, these 2 atoms can link together, okay, and form a neutral charge. Okay? And so that's where the opposite electrical charges would come into play, and they're attracted to each other. Now, when they're most stable, they're often in a crystallized form. Okay? So things that form crystals are often, okay, not always, the result of ionic bonds. The other thing about ionic bonds is they're relatively weak. So here you can see a sodium atom, okay, with a positive charge, okay, and a chloride atom, okay, or a chloride ion, okay, with a negative charge. So the chloride has an extra electron, the sodium ion has lost an electron, okay, But when you put the two together in solution, they'll form salt, or NaCl. Okay? And they'll get their most stable form, okay, when they're in a crystallized structure like this shown here. Okay? Now, covalent bonds are far more strong than ionic bonds. Ionic bonds are relatively weak. And so what does that mean? It means that they're easy to separate, but because the force is very weak that's holding them together, there's not much energy as a result of separating them. Okay? Covalent bonds are when atoms share electrons, okay, between the two nuclei of the atom. Okay? And you know, this is where you get information like double bonds and triple bonds and things like that. Is really based on how many electrons are shared between the two atoms. Okay? If it's a single electron, then it's a single bond. If it's 2 electrons, it's a double bond. 3 electrons, triple bond. Okay? And so on. But most of the time we stop at that. Okay? And so really this is based on just some of that information we talked about before about the electron shell, that outside orbital trying to be full of electrons. Okay? Now, covalent bonds are stronger than ionic bonds, okay, because the electrons shared sometimes equally between the two nuclei, but sometimes it's not equal. Sometimes one nucleus has a stronger electronegativity, so it pulls the electron closer to that nucleus. Okay? But nonetheless, there's an electron that's being shared, okay? And we're not just basing it on opposite charges. So here you can see just a few examples of covalent bonds. Okay? The formation of hydrogen gas, you can see they're sharing electrons. Methane gas, again, electrons shared. And here's a double bond to form oxygen, okay, in which they're sharing 2 electrons. Okay? And we'll come back and we'll talk about what happens when you separate these molecules and where's the energy coming from and whatnot. Okay? Now, like I said before, in a covalent bond, they're sharing electrons, but the electron sharing doesn't have to be equal. Okay? And when it's not equal, so when one nucleus attracts the electron or has more pull on the electron, it's considered a polar molecule. Okay? Which means that one side of the molecule is going to have a negative charge and the other side of the molecule is going to have a positive charge. Okay? And again, whether this occurs or not will just really depend on the electron negativity of the atoms that are involved in forming the molecule. Okay? If they both have the same electronegativity, the molecule is not polar. But if one molecule, or if one atom has a strong electronegativity, a much higher electronegativity than another, then often it will result in a polar molecule. Okay? This also depends on, you know, how many bonds are formed, and how many electrons are needed to fill that outer shell, and a bunch of other factors that can play. Okay? But nonetheless, if one nucleus is pulling the electron closer to it, it's going to cause a charge on that molecule. Okay? So again, just to kind of recap, this will cause the molecule to be what we call polar, which means that one side will have one charge and the other side of the molecule will have a different charge. Okay? And it's really due to that unequal sharing. The electron is spending more time with one atom on one side and less time with the other atom on the other side. So any given amount of time, okay, the side that's got the electron most often is going to be negative. The side that has the electron least is going to be positive. hydrogen bonds are kind of a unique situation, okay, which is really the result of a hydrogen ion or hydrogen forming, okay, a bond between the positive end of one molecule and the negative end of another molecule. This is often the result of water. Okay, now water is a covalent bond, but the hydrogens attached to water will often form hydrogen bonds. This is what makes water what we call the universal solvent, okay? Because hydrogen can bind with things that are in a negative state, okay? And so water can often bind with lots of different things that are polar molecules. So if it's a polar molecule and it's going to have a positive and negative charge, then hydrogen can bind to the negative end, okay, of whatever that other molecule is. Or it doesn't have to be a different molecule, it could just be water. Water can form hydrogen bonds with itself and does so often, okay? And this is how we get the formation of ice. Okay? Now hydrogen bonds by themselves, okay, are really weak. But because hydrogen is such a small atom, it often forms a huge number of hydrogen bonds when in solution. So it'll often form as many hydrogen bonds as possible, filling as many, orbitals or filling the need for as many electrons as possible. And so by itself, it's true, hydrogen bonds are very, very weak. Okay? But in a collective force, they can be very strong because they are going to maximize the number of bonds provided. This is also hugely important when we start talking about energy, because the more bonds you have, the more potential energy you can get. So if we're talking about molecules that are just full of hydrogen bonds, okay, they typically have a high amount of potential energy, because every time you cleave off one of those hydrogen bonds, you have the opportunity to utilize the energy that comes from breaking that bond. So again, just kind of a simple recap, okay? The additive effect of hydrogen bonds can make it very strong. For example, the molecule I showed you at the beginning of this little piece of lecture, DNA, the bond between the nitrogenous bases that occur in the middle of DNA, okay, between adenine, thymine, guanine, cytosine, are hydrogen bonds. Okay, between adenine and thymine, there are 2 hydrogen bonds that form. Between guanine and cytosine, there are 3 hydrogen bonds that form. Okay, and so again, by themselves, very simplistic. But when we're talking about, in the case of humans, okay, 3 billion base pairs in our genome, okay, and you might have in a segment of DNA, say on a single chromosome, okay, you might have 1 million to 100 million, depending on the size of the chromosome, okay, maybe even a little more, nitrogenous bases that are bond together. Okay, that's a lot of bonds. We're talking 2 million bonds, 3 million bonds, depending on how many adenine, thymine, cytosine, guanines you have along that segment of your DNA, along that chromosome of your DNA. You have a lot of forces holding that DNA together, making the molecule really stable. And we'll come back to DNA later. Okay. So here you can see just an example of the formation of a hydrogen bond. So you have this molecule here, which is a carbon chain, okay, with hydrogens off of it. Okay, this is a covalent molecule or covalent bonding molecule, okay, with an OH group off the end, or hydroxide off the end. Now, because this right here is going to be polar, okay, this hydrogen here is going to have a positive charge, it can then form a hydrogen bond with a water molecule. So that allows for this to go into solution of water. Okay? And this is how we get things to dissolve into water. They form simple hydrogen bonds. Okay? And polar molecules are the molecules that are going to go into solution in water or be dissolved in water. Okay? So this kind of brings me to what gives water its unique properties. Okay? And a lot of that comes from hydrogen bonds. Okay? And the fact that we know that water is essential for life. This is why, probably one of the biggest reasons NASA even exists is for us to explore outer space, the universe, to find out if there is life elsewhere. Okay? And we're almost always looking for water. Okay? I mean, if you see a report about, a Mars rover or pictures of a moon off of another planet, okay, it's almost always in context to, is there water? Okay? And that's because as we know life on this planet, water is essential. Okay? Now that's not to say that that's the case everywhere, but we're not going to hypothesize or even explore those issues because there's no evidence for anything other than water life. Okay? We know that there are large groups of individuals and even entities that are exploring the chemistry of water, okay? And how we can better remove pollutants, how we can better utilize water that hasn't been utilized before. Desalination, okay, so how can we without burning up the ozone and burning up all our coal and natural gas supplies, how can we get to some of the ocean water? Okay? And it's not that we're running out of water. Okay? The amount of water on the planet hasn't changed in 4.6 billion years. It's the same amount of water. Okay? So yes, the water that you're drinking today could have been also consumed by a dinosaur 300 million years ago. Okay? Now, the issue is not water molecules, the issue is clean water. Okay? And that's the main issue that we're having today on the planet is we don't have enough clean water sources. Okay? There are about 1 billion people on the planet that don't have a clean water source. Okay? And even more than that, like around 2 billion people on the planet that don't have any sanitary solution to water. So their water becomes dirty because of sanitation, in the sense of either washing your clothes in drinking water or going to the bathroom in water sources, watering your crops with the same water you're drinking, and with runoff and all these other issues. So water is a huge issue in today's society, not just in the United States. It's a big deal in the United States, okay? But it's also a much bigger deal in a lot of other countries, okay? And so the chemistry of water is being studied all over the world, okay? And trying to figure out better ways to clean water, safer ways to utilize water for the future. Okay? Now, back to the chemistry of water. Water is a polar molecule, like I said before. So the hydrogen portions of the water have a positive charge, and the oxygen portion of the water has a negative charge. Okay? This allows for it to form hydrogen bonds. Okay? And because it can form hydrogen bonds, it can be that universal solvent, form hydrogen bonds with all other polar molecules, but it also can form bonds with itself. Okay? And that piece right there is what gives water a very unique property, or very unique set of properties. Okay, some of which is the following. So the heat storage property of water, okay, is the ability for it to change slowly and hold temperatures well. Okay, and because of this, it really allows for the planet, for Earth, to maintain fairly stable temperatures. We see much larger fluctuations of temperatures when we look at other planets that don't have water. Okay, that when the solar radiation is coming into the planet, it heats up really fast, gets super hot. Okay, and then when the solar radiation is gone, that portion of the planet cools down extremely fast and gets really cold. Okay, in the case of our planet, Earth, okay, this process is slower. Okay? Yes, our temperatures rise when the sun's out, okay, and decrease when it goes away, but our temperatures are maintained and held much more stable. And a lot of this is because, roughly 70% of the Earth's surface is water, okay, that can slowly change temperature and hold temperature well. Okay. The other huge one, probably the biggest piece, is ice formation. At least the biggest piece for life on the planet is ice formation, and the fact that water is most dense at 4 degrees Celsius. Okay? So if you have water that's 4 degrees Celsius, and then you cool the water to 3 degrees Celsius, okay, what'll happen is the 4 degrees Celsius will go to the bottom. Okay, it'll fall, okay, because it's more dense. Okay? This is what happens with lake turnover. Okay, so in the fall on big lakes, you'll probably see the lake becomes really murky and muddy looking, and that's because the lake is turning itself over. Because the surface water, as temperatures cool, okay, as you progress towards winter, temperatures cool, okay, the surface temperature of the water becomes closer to 4 degrees Celsius. When it hits 4 degrees Celsius, it becomes more dense than the water below it that might be even colder. It might be 3 degrees Celsius or 2 degrees Celsius. And so or it could be a little bit warmer at 5 degrees or 6 or whatever the temperature, it really doesn't matter. Because once the water hits 4 degrees Celsius, that water goes to the bottom of the lake, okay, sits on the bottom of the lake, okay, and that process of change in water fluctuation or movement of water causes the lake to do what we call turnover. We have a fall turnover and we have a spring turnover. Okay? And it causes nutrients to move throughout the lake. And this is a great property to vitalize the lake's nutrient levels. So plants along the shore can start absorbing nutrients, fish can consume things, microorganisms can consume things, okay, all kinds of situations. But the big kicker with ice formation is ice, okay, is less dense than that 4 degrees Celsius. So the ice floats. Okay? This is a great property for having life, because almost all the evidence that we have suggests that life started in the water, okay, a long time ago, 3.5, 3.6 billion years ago. Okay? Well, if ice was more dense than liquid water, when ice would form on the surface, it would sink to the bottom, and you would not be able to have any life. It would crush out the life below. And this would be especially true for lakes and things like that. And even though the oceans may have not froze solid everywhere, but there are times on the planet when it was cold enough that huge swaths of the ocean would have froze, and life would have been stamped out in all those regions. So you might have a really teeny narrow band that might have been able to live. But still at that, once any of these organisms made it to a situation where they were away from the equator, away from stable temperatures, okay, again, it would have froze and killed them. Okay, so that's a huge property to have, and allows for life in freshwater systems to exist, but also in Arctic systems to exist, and really plays a major part on the life on this planet. Okay. And the final one really has to do with the high heat of vaporation, okay, or vaporizing water. Okay. Now, the great things about vapor water, or the properties of having vaporized water, are things like, when plants heat up, they can transpire, okay, which means they release water vapor into the atmosphere. Okay, that can come back to the terrestrial habitats in the formation of rain, or aquatic habitats in the formation of rain. Okay, that vapor allows for evaporation to occur and allows for the water cycle to be maintained. The other things that vapor can do, though, is you can get evaporative cooling. Okay, and this is often present in most living organisms. Most animals go through evaporative cooling, where they're losing a little bit of water, but they're losing it into a vapor form, which condenses a little bit and cools them in the form of sweat, okay, or panting in animals, or just the loss of a little bit of water, okay, to maintain a stable environment. Okay? And we'll approach that one again when we start talking about evolution of different organisms and different systems. Okay? So here you can see ice formation and what I was talking about with density. Density is just a measurement of how tightly packed molecules are. So here you can see water, okay? And this is probably at maybe 4 degrees Celsius because it's fairly densely packed, okay? And they're really jumbled together, okay? And then you can see water in the ice form, okay? Where these molecules are spaced evenly or fairly evenly apart from one another. And they're not dense, they're not as dense as this, therefore this floats on top of this, okay? And that over there would sink, okay? And that's the premise behind density. Okay? It's just how tightly packed a molecule is. Other unique properties that hydrogen bonds really give to life in general, but unique properties that allow for life to exist, is the property of cohesion, which is the attraction of water molecules to other water molecules, and is really the premise behind drops of water and what really gives us raindrops. Okay, and without it, we would, the terrestrial system would be an arid desert, okay, because you probably would never get enough water on to the landscape to have anything but deserts. Okay? And so that cohesion, that attraction of water molecules to other water molecules, is very important. It also gives a added aspect or an added niche for some organisms. Okay, so you can get surface tension that can form on bodies of water. Okay, for example, this water strider here is utilizing that cohesion force. Okay, so the fact that water is attracted to other water molecules, you can see here that this organism can walk on top of water. Not only walk on top of water, this organism, water striders, live on top of the water. They utilize that niche. They breed, they feed, they sleep, they do everything on top of the water, on that surface tension piece of the water. So it adds an ecological niche, and we'll talk about this when we get to ecology. The other piece is adhesion, or the attraction of water molecules to other polar molecules. Okay, not only is this going to allow for things to dissolve in water, which means nutrients can move throughout the ecosystem, but it also allows for things like capillary action. I mean, to put this in perspective, think about the redwood forest, okay? And you think about trees in the redwood forest and the height of the trees. I mean, I think on average some of the biggest trees are around 350 feet. Okay, I think the calculation based on properties of water and whatnot has really limited trees at least the last calculation I saw, was about, no tree could really get over about 450 feet because of the properties of water. Well, what properties of water are they talking about? They're talking about cohesion and adhesion versus the force of gravity. Okay, so this attraction of water molecules to other water molecules, but also the attraction of water molecules to other polar molecules, allow for trees to use capillary action to get water from the roots all the way 350 feet up into the canopy, okay, by using these forces. Right? It's pretty amazing to think that it just takes a little bit of chemical properties in order for that to occur, versus something like, having a giant heart. If you're 100-foot, tall dinosaur, you'd have a massive heart in order to pump blood from your toes to your head. Okay? But trees do it with just a simple chemical property, or hydrogen bond property. Okay? So we're going to stop there. We'll talk more about molecules. Okay? We're going to talk about biomolecules, so molecules that are specific to kind of life, and the importance of these molecules to energy, okay, and the importance of these molecules to building bodies, importance of these molecules in cycling through ecosystems, etc. Okay, so till next time, have a good one.